Okay, so first of all, thank you so much for having us. So I'm going to be talking about the threshold test. Claims of biased decision-making occur in a wide variety of domains, from lending decisions to hiring practices and policing. However, oftentimes the ability to assess these claims is it's very difficult to assess these claims due to the limitations of current approaches. What Sam and I are going to be presenting today is a novel test that mitigates some of these limitations and introduces a test that is able to identify and measure bias in decision making. And this is joint work with Emma and Shard Goel at Stanford. Okay, so we're going to focus on the context of policing, and namely traffic stops. And to give you a sense of the scale of the issue, in the US alone, over 20 million traffic stops occur annually, making this the primary way in which the public interacts with law enforcement. Now, there's concern of racial bias in police actions, and as with many of the other domains, it's often very difficult to assess the extent to which these claims are true, because seemingly reasonable tests of discrimination can often lead to very misleading results in practice. So we develop what we call the threshold test to measure racial bias in officers' decision to search drivers. And the question we want to answer is, are minorities subjected to a search on the basis of less evidence than whites? And we do so via a Bayesian hierarchical latent variable model. Okay, so we empirically validate the model on a data set of 4.5 million stops in North Carolina. This is over a six-year period from the largest 100 local police departments. And we consider 3 race groups: white, black, and Hispanic drivers. Just to give you a sense of the data, search rates typically vary from 4 to 8% for whites and minorities, respectively. Okay, so just to, in order to kind of understand what the threshold test is doing, I'm first going to briefly go over a standard test of discrimination and show you how it can fail. The most widely used test today is known as the outcome test, which was proposed all the way back in 1957. The test compares search success rates, or hit rates, across different race groups. So the idea here being that if searches of minorities systematically turn up less contraband than searches of whites, this is suggestive that officers might be applying a double standard, searching minorities on the basis of less evidence than whites. So in North Carolina, here we have each point in the plots is a department. The x-axis is the white hit rate, and the y-axis is the minority hit rate. And points are sized by the number of stops. So we noticed that for black drivers, there is some evidence of this occurring for some departments, and for Hispanics, this is significantly more biased. So there's much more evidence of bias for Hispanics. Yep. So this seems reasonable, right? It turns out that this test suffers from a well-known limitation called the problem of infra-marginality. And if you've been following sort of the discourse on fairness, a lot of these algorithms, this occurs in a lot of these algorithms as well. So what is this? To see this, let's think about what happens during a typical traffic stop. So an officer will stop a driver. They will observe any number of factors, right? So the race, gender, time of day, location, and they'll look for cues. So signs of evasiveness or nervousness. And they somehow have to use all of this information to make a binary decision of whether to search or not. So we imagine that they distill all of this information down into a single probability estimate of the risk of the driver, so the likelihood of possessing contraband or something illegal. And as more and more drivers are stopped, we can build distributions over the risk or likelihood of possessing contraband of each race group. And we can imagine that, or we would imagine and hope that any drivers above a certain level of suspicion would all be searched, right? So anybody above the search threshold would get searched. And now to see how this can fail, let's take an example with 2 race groups, red and blue. So here discrimination is occurring against blue drivers by construction because blue drivers are subject to a lower threshold than red. So somebody, a blue driver with a 25% likelihood of having contraband would not have been searched had they been red. Right, but if we calculate the search rate and the hit rates, we can see that red drivers actually are searched more and have a lower success rate of those searches. So the outcome test not only fails to identify discrimination against blue, but actually goes the other way and suggests discrimination against red. So the reason here is because of the heavier tail in the blue distribution, right, which is driving up the hit rate. And the sort of key takeaway here is that what we're trying to measure is we're trying to compare the drivers with similar levels of suspicion and compare their outcomes. But we can't actually observe these. So we can't actually observe these like marginal drivers. We can only observe the aggregate outcomes for the whole group. And these aggregate rates are sometimes very poor proxies for the marginal outcome. Especially when the risk distributions vary so much by race group, which is not unreasonable to think of. So what the threshold model does is actually goes and we infer the actual thresholds and search and risk distribution parameters. So to formalize the generative model, we have an officer in Department D who's stopping a driver of race R. Each driver has some kind of risk of possessing contraband. And this is xi, which is drawn from a beta distribution. And we allow these distributions to vary by race and department. Okay, the officer deterministically conducts a search if xi is greater than the threshold for that race and department. And if a search is conducted, then a hit, so a successful search, occurs with probability x. And lower thresholds will indicate discrimination. Okay, so the risk distribution has a fairly intuitive interpretation. So it has a race and a department effect. And phi here represents the probability that a randomly stopped driver is carrying contraband. And lambda will capture the difficulty in distinguishing between guilty and innocent drivers. So is sort of a measure of the variance of the distribution. And now the number of observations in our case equals the number of stops, which is in the order of millions, oftentimes. So a naive inference of the posterior of the parameter distribution is very intractable. So instead of modeling the stop level outcomes as Bernoulli variables, we switch to an alternative parameterization, instead modeling the aggregate, the total number of searches and the total number of hits as binomial variables. So in this case, the search rate is the probability of x being above the threshold, and the hit rate is the expected value of x conditional on being above the threshold. Okay, and we can represent this as a graphical model where the total number of searches and hits are the observable cells at the bottom, and we are inferring the thresholds and the risk distribution parameters.
All right, so there's one downside with the model as we've laid it out so far, and that is that inference can take a really long time. So to compute the derivatives of the log posterior requires these complicated derivatives of beta conditional distribution functions, and as a result, in North Carolina, I think inference took about 2 hours. We're trying to extend this to bigger states or to a nationwide analysis, and it becomes intractable once you consider all the robustness checks you have to do an analysis like this. So we started looking for an alternative to the beta distribution that had better computational properties. So I'm going to lay out a slightly different generative model now that speeds up the threshold test. So imagine first that we draw whether a driver is carrying contraband. So we draw that from a Bernoulli distribution, and then drivers give off some signal as to whether they're carrying contraband or not. You can think of this as sort of like some sort of suspiciousness index, right? And innocent drivers give off a certain distribution, so it's in the red here. And guilty drivers give off a different, normally distributed signal. So the signals given off by the whole population of drivers is this mixture of Gaussians. Now for any x, for any signal, we can ask, what's the probability that a driver with that x is carrying contraband? And we'll call that z. So these risks, z, we'll also have a distribution. And that'll be distributed on 0, 1, of course. And it's going to be based on 5 parameters, right? It depends on P, the probability that a random driver is carrying contraband. It depends on the mean and variance of the innocent distribution, the mean and variance of the guilty signal distribution. So there's your 5 parameters. You might recognize this setup as very similar to linear discriminant analysis. And in fact, Z is the distribution of all predictions from a one-dimensional LDA. And much like LDA, we require that the mixture is homoscedastic, has the same variances, and that means that there's a monotonic mapping between X, the signal that a driver gives off, and their risk, the probability that they're actually carrying contraband. Once we make that constraint, the distribution of Z, the distribution of the risks, only depends on P, the probability that a driver is carrying contraband, and this delta, which is the normalized distance between the guilty mean and the innocent mean. So without loss of generality, we can define the innocent distribution to be a standard normal distribution, and the guilty distribution also has a variance of 1, but has a mean of delta. So now we have a 2-parameter family of distributions supported on 0, 1, so maybe we can swap out the beta distribution for this new family of distributions. And we've called this family discriminant distributions with reference to LDA. And what do we get from doing this? Well, it means that all the computations we need for the threshold test are now simple functions of the Gaussian CDF. So the search rate is just a fraction of drivers with risks above the threshold. What we can do is use the inverse transformation to turn the threshold from probability space to signal space and do all the calculations in signal space. And therefore, the search rate is just the sum of the fraction of guilty drivers who are over the threshold plus innocent drivers who are over the threshold. Similarly, for the hit rate, it's the fraction of guilty drivers above the threshold divided by the fraction of drivers above the threshold. And doing it this way results in a huge speed up. So gradient computation is 50 times faster. We also need fewer gradient computations per sample. So it suggests that Stan finds it easier to sample the posterior when it's formulated like this. So we get a 150 times speed up in inference in the model. What took a couple of hours is now less than a minute. We also get more effective samples per sample, so you conceivably have to run this for fewer iterations. And what this means is that the threshold test can now be practically used for a wide range of investigations into discrimination in various contexts. So to talk about some results with this model, in North Carolina we find that black and Hispanic drivers face lower threshold than whites, a significantly lower threshold. So white drivers aggregating over all departments. This is face a 23% threshold. For blacks it's 20.6, for Hispanics it's 14%. We can dig a little deeper into the department by department results. We see that for Hispanic drivers, the threshold is lower in almost every department. So here on the x-axis is the white threshold. On the y-axis is the minority threshold. The departments are sized by the number of stops. For black drivers, there are some departments that apply approximately the same thresholds, but there are also a number of large departments where we see black drivers facing lower thresholds. We run some posterior predictive checks. So we generated data according to the parameters we inferred and determined the inferred search and hit rates and compared those to what we actually saw. We see that the model fits search rates very well and hit rates also quite well. To conclude, we developed a Bayesian latent variable model that allows us to directly estimate the thresholds and provides a solution to the problem of infra-marginality that affected other tests for discrimination. We find unjustified disparate impact against Hispanic and African American drivers in North Carolina. And there are very few legitimate reasons that there might be different search thresholds. So for example, we can rule out, say, officers applying lower thresholds at nighttime and minority drivers having different driving patterns. One thing we can't rule out is if drivers carry different types of contraband. So officers might be applying a really high threshold for marijuana because they don't really care about finding a low-level drug like marijuana, but they might apply a very low threshold for weapons. And if different groups carry these different types of contraband at different rates, that might drive some of the difference in thresholds that we see. We can't rule that out. Our test also can't distinguish between implicit bias and explicit bias. So explicit bias is when officers are consciously applying lower standards to minority drivers. Implicit bias is when they're consciously applying the same standard, but they're systematically overestimating the risk of minority drivers carrying contraband. And these two different types of bias have different policies prescriptions, but they appear the same in our model. Finally, I just want to pitch our project, the Stanford Open Policing Project. Camelia and I and a few other colleagues at Stanford have been working for a couple of years, FOIAing different state police departments, cleaning that data up, and we've now made it all public. So if you go to openpolicing.stanford.edu, you can download data sets of traffic stops around the country. I think we have 21 states, although we did ask everyone, and we've had various interesting encounters with different FOIA officials. There's about 100 million police traffic stops there, and we're really interested to see what a community like this can do with a data set. So thanks very much. And the papers are there if you're interested in reading more. So if there's time for questions, we'll take some otherwise.
All right, questions? Oh.
Just curious about the heteroskedasticity assumption. I mean, is that valid?
So if you don't have that, then there's values of X. You can imagine really low values of X where there's a high chance, again, that drivers are carrying contraband. So to ask whether it's valid is almost, we use that to derive this two-parameter distribution, and without that, it doesn't. It's not a. There's no mapping from risk to. From the signal to the risk, and so you couldn't form that two-parameter distribution.
Other questions? Jonah, you have to belt it out.
We've sent it to a few police officers, and they're relatively skeptical, I would say.
Yeah, I would say that's true. I mean, it's also difficult for them to understand maybe some of the statistics behind it, and so they're can be somewhat skeptical of what is going on in this black box model.
Yeah, that's who we're mostly talking to right now. The criticism we get from police officers is like, well, we go into these communities and there are high crime rates, so we should be. But that's not an argument about thresholds, right? It's an argument that the distributions might be different, which we completely allow for in the model, but there's really not a good justification for why thresholds should be different in that case.
Any other questions? Oh, Charles?
So I was wondering about one of the plots you showed, and maybe I'm misreading it, where you show the thresholds for arrest, and you benchmark it against a threshold for white people, and it seems that if we look at the arrest threshold for black people, it almost aligns.
Yeah, right. Yeah, so we don't find huge differences for black drivers in North Carolina.
So whereas for Hispanics, something more significant seems to be happening. So do you think that the difference you observe for black people could be related to noise? And also, have you compared these results to other results, other studies that have been conducted on the subject? Because I'll admit that the plot on the left surprises me a little bit. I would expect a more significant
the extent
threshold.
to which I think we find in a lot of, so we now have done these sorts of analyses in the 20 states that we have data for, and I think it surprised us as well, but relatively consistently we find greater discrimination against Hispanic drivers. I think that's fair to say.
And also, actually what surprises me is I don't know if I can interpret this as little discrimination against black people or not. Or do you think
it's hard to sort of put a magnitude on it?
Okay.
And sure, if you can, under the model, you can kind of estimate how many searches might not have happened had they been treated as if they were white drivers, and it's thousands of searches. So it's like, but
okay, yeah.
So it's important, but the effect against Hispanics is much bigger.
Okay, cool. Thank you very much.
It's quick.
And just to add, I think something we didn't really have time to go into is we do see this effect of infra-marginality actually being a real-world problem that comes up in the data set. So we're able to kind of hone in on various departments and kind of see this actual heavy tail for, one of the minority groups which the outcome test doesn't pick up. So although those differences might be subtle, like, for, let's say, for blacks in this case, it's a much finer test that's able to kind of like pick at this, this problem with the other tests.
So one more question.
We're about to run a recording,
right.
so I'm